This video is going to continue our exploration into electromagnetic radiation, and in this video we're going to discuss the relationship between electromagnetic radiation and energy. For a quick review, remember that EMR can be seen either as a wave or a particle, depending upon how you observe it, that waves are an oscillating function and they deliver energy. As far as waves go, we are concerned with two measurements. The first is the wavelength, distance from peak to peak, and the frequency, how many waves pass a fixed point in 1 second. The former is called lambda, the latter is called nu. And for electromagnetic radiation, lambda times nu, wavelength times frequency, equals the speed of light c, which is 3.00 times 10 to the 8th meters per second. We're going to be talking about the particles of light in this video, and light particles are called photons, and yes, these are the same photons that make up the photon torpedoes in Star Trek. Now you can think of photons as small discrete packets of wavelengths, so they will deliver energy. This is only a model, it's not really true, but as we showed in the atomic modeling section, models can work. So photons are massless packets of energy. And the equation that's used is E equals h nu, where E is equal to the energy in joules. Joules is named after James Joule, a Scotch whiskey maker in the 1800s. H is Planck's constant, named after Max Planck, a physicist in Germany in the early 1900s. And Planck's constant is 6.63 times 10 to the minus 34th joules times second. And this is a constant, so it never varies. And nu is the frequency, and once again the unit is seconds to the minus 1, photon to the minus 1. This calculates, well, the equation calculates the energy of one photon. Now, h is a constant. It never changes, so I believe you can understand that that means that E is directly related to nu. Energy and frequency are directly related. If the energy goes up, the frequency goes up. If the frequency goes up, the energy goes up. Conversely, the energy goes down when the frequency goes down. The frequency goes down when the energy goes down. Now go back to the earlier equation that you know, C equals lambda nu. We know that lambda and nu, wavelength and frequency, are indirectly related. If one goes up, the other must go down. Therefore, energy and wavelength must also be indirectly related. So as energy goes up, wavelength goes down. As wavelength goes down, energy goes up. The smaller the wavelength, the higher the energy. So high frequency waves are high energy waves. Low frequency waves are low energy waves. And since frequency and wavelength are indirectly related, high frequency waves are high energy waves, which means that you must have a small wavelength. Low frequency waves have low energy, and due to the inverse relationship between frequency and wavelength, low energy waves must have a large wavelength. What this means is that every specific frequency has a very specific energy and a very specific wavelength, so that any objects radiating the same color are radiating photons of identical energy. So anything that is red hot, each photon has the same energy, whether it's the coil on a stove, red hot iron, or a red laser. The only difference is the number of photons being delivered in a given time. This also means that different colors have different photon energies. So the energy of a red laser is different than the energy of a violet laser, which is different than the energy of a green laser. And if you take a look at the chart that we had in the previous video, we see that red light has a longer wavelength than the violet light. Green is somewhere in the middle. So that red light has a smaller frequency. The violet has a larger frequency. So if you want to arrange the lasers in order of highest to lowest energy, the violet laser contains more energy per photon than the green laser, which contains more energy per photon than the red laser. So now we can do calculations. So here's the first example. You have a photon of light with a frequency of 5 times 10 to the 14th hertz. What's the energy? Well, once again, what do we know? We know that energy equals h nu. H is Planck's constant, so it's a given value. The frequency stated above is 5 times 10 to the 14th hertz or per second, and E equals E. Plug everything into the equation, and you get 3.32 times 10 to the minus 19th joules per photon. This is an exceedingly small number. It's 0 point and then 18 zeros followed by the 332. Any one photon has very little energy, but there are gazillions upon gazillions upon gazillions of photons, even in a very small burst of energy, and they do add up very quickly. So let's go to example 2. A photon has an energy of 8.98 times 10 to the minus 12th joules. What is the frequency of this photon? Once again, what do we know? We have our energy equation. We know that what the energy is per photon. We know Planck's constant. We don't know the frequency. Set the equation up, plug and chug, and you get 1.35 times 10 to the 14th hertz as the frequency. Okay, let's go to example 3. Violet light has a wavelength of 425 nanometers. What is the energy of a photon? What do we know? Well, E equals h nu. Here, the energy is unknown, so E equals E. H is a constant, so we know that value, 6.63 times 10 to the minus 34th joules per second, and nu equals nu. We don't know the value of the frequency. So now we have one equation with two unknowns. So obviously this can't be solved. But wait, we actually know more. What else do we know? C equals lambda nu. C equals 3 times 10 to the 8th meters per second. The wavelength is 425 nanometers. We either need to convert the wavelength to meters, or we need to convert the speed of light to nanometers. I prefer to do the former. So we go 425 nanometers times 1 meter per 1 billion nanometers, and the 425 nanometers becomes 4.25 times 10 to the minus 7th meters. The frequency is the frequency. Set everything up, solve for the frequency, and it turns out that this violet light has a frequency of 7.06 times 10 to the 14th per second. Now we can go back to the original set, and we can change our third line here, because now we know the frequency. 7.06 times 10 to the 14th hertz. Plug this into the equation, and you get 4.68 times 10 to the minus 19th joules per photon. Now, one final example. You have two types of electromagnetic radiation. An X-ray, which has a wavelength of 1.5 times 10 to the minus 2 nanometers, or an ultraviolet ray with a wavelength of 1.3 times 10 to the first nanometers. Which one is more energetic? Explain it, and you can explain it either using words or a mathematical explanation. Go. The answer is the X-rays. If you did it mathematically, you would just run through the equations like we did in example 3. I'm not going to do that. But you can explain this verbally. X-rays have a smaller wavelength. Smaller wavelength means higher frequency. Frequency and energy are directly related. So the higher the frequency, the higher the energy. Therefore, since X-rays have a shorter wavelength than ultraviolet rays, the X-rays must have a higher frequency, which means the X-rays have more energy. So to review, energy is equal to Planck's constant times the frequency. E equals the energy in joules per photon. Planck's constant is 6.63 times 10 to the 34th joules per second. I will always give you that value. And the frequency is nu with these units. Energy and frequency are directly related. Energy and wavelength are indirectly related. So the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. The smaller the wavelength, the higher the energy. The larger the wavelength, the smaller the energy. So as we go dashing into the final lecture of this section, we're going to try and put this all together and discuss how elements can have fingerprints.